Welcome, class. We're going to look at first section of chapter 1 here. We've done the review. You've gone through looking at similar triangles, and you should have, at this point, understood that the ratios of particular side lengths, opposite hypotenuse, and opposite adjacent, are connected or tied to a particular angle in a triangle. And that angle has locations which can change, and the value of course can change depending on the shape of the triangle, and this is a unique ratio for every angle. Regardless of the size of the triangle, the ratio is unique, which means it's its own value, different from other shaped triangles. So today we're going to look at just a lesson going through the sine, cosine, and tangent values that are connected to these ratios. And you've seen this before, so we'll go through this first slide pretty quickly. Of course, these ratios can only be used for right triangles. Just again reviewing the different ways of labeling triangles. We've got vertices, which are the corner locations for the triangle, quite often just labeled A, B, C, and you can use a two-letter symbol with both vertices included, and that would define a side. So for example, BC is this side here, which is across from vertex A, so we also label that little a. So that we'd seen before in a previous lesson. Let's keep going here. Here's an instrument which we're going to try to use in class. You may have used this before in a previous course with the trig unit. It's called a clinometer, or also known as an inclinometer. And that's exactly what it does. You hold it on an incline, or possibly a decline, depending on what you're trying to cite. It could be something above you or below you. And you're measuring a particular angle using more or less what's a protractor mounted on a pivoting disc. And this outlines the steps of how you would use this instrument. So we'll go through this with an outdoor activity where we can measure something that would be pretty hard to directly measure as far as the length. So here we're going to be measuring a vertical distance between your ground and eye level. That's important because you're holding it off of the ground, so you'd have to add that to the calculated height. You're going to be measuring the distance between the object and you horizontally, and then what you're trying to do is you're trying to construct information from a triangle. So if the object is inaccessible, like a very, very tall tree or building, it's easy enough to pace yourself away from the base of it, and that would represent this horizontal distance here. And then you've got this extra little bit here from the ground up to your eye level, which you need to know about. And then it's simply a matter of measuring an angle, which could be your angle of elevation here. So that gives you two pieces of information for the triangle, and then using trigonometry principles you can solve that right triangle, because you would be able to use likely the tangent ratio by involving the opposite side and the horizontal, which would be the adjacent. And at that point you'd be able to find the height using a quick calculation and then add on that extra little bit. So that's the method that a clinometer depends on. And in this case, this triangle is a right triangle because, well, most things that are built off of the ground are at a 90-degree angle to the ground. So that's what allows us to use right triangle principles. Okay, so that's an introduction to the clinometer. A couple terms you're going to come across in this lesson. You should have seen these before. They may be a bit of a review as well. Let's say you're sighting a plane up in the clouds or a boat down in the water and you're standing on the edge of a cliff. In each case, there's this imaginary line of sight directly horizontal from your eye, and the angle of inclination or elevation or the angle of depression are measured relative to that. So one goes up, that's the elevation angle, and one goes down, that's the depression angle. And so there's the definition for you to have a look at to tell them apart. There's a whole process here that we can maybe sum up at the end of this. Things that you need to know how to do in order to be successful at solving for sides and angles in a right triangle using trigonometric ratios. You can have a look at this now and maybe compare it to the things that you already know how to do and see if it's almost like a checklist. Do you use a visual? Do you look for an unknown? Do you select the correct ratio? that involves the known and the unknown side lengths. Do you write the equation that relates that information, and then do you finally solve with an appropriate an amount or a unit? The alternative is possibly if you're solving for an angle, the solving step may require some inverse operation. We're going to look at those as well today. So I'm just going to go through about 4 examples here. I'm not going to fully solve them, but I'm just going to show you what are the general steps are you need to take in order to solve a triangle or solve for a property in a triangle. And I'm going to leave it up to you if you want to complete the calculation to do so, and then just get comfortable and confident with solving for different parts of a triangle. Okay, so these are just simple triangles. There's no context here. There is a unit, so we want to make sure we stay consistent. If we are answering at length, it should be in meters for this example. What are we being asked to solve for here? Well, it's this solve, because that's sort of this broad term which means find everything about the triangle that you can. Okay. Well, the only thing we do know right now is we have LK and we have angle K. So we can write that down. Angle K is 30 degrees. We have side LK has a length of 210 meters. And if we were to solve for everything else, well, there's JL, which is not known. There is JK, which is not known. And then, of course, there's angle L, which is 90. That's known. So actually from that, we should be able to say that angle J would be 180 degrees, subtract the other two, which would be leaving us with 60 degrees. So that's part of the solution right there already figured out. So that gives us all of the angles in the triangle. And then it's a matter of solving for one of the other two sides. And then we could use Pythagorean theorem to solve for the third. So I'm going to choose to use angle K. And I'm going to try to solve for side length JL. So what I'm going to do is I'm going to set up a ratio here. And of course, relative to angle K, JL is the opposite, LK is the adjacent. So I'm going to label these on my triangle. And I'm just going to circle the vertex to indicate that this is my chosen angle, or my chosen vertex. So a 30-degree angle. Right, so if I'm using opposite and adjacent, that would be the tangent ratio. So I'm going to write tangent, which is an operation done on an angle. It is equivalent to a ratio of side lengths. The opposite side and the adjacent side is what tangent means. And in this case, the opposite side is not known, so I'll write JL, and LK is 210. So from that, I can solve for JL. I'll multiply both sides by 210, and that would leave me with just the value of JL. Okay, so this needs to be calculated, so I'll leave that with you. Once we have that done, we should be able to, I'll state this, solve for JK using Pythagorean theorem. And that would look something like this. JK squared equals JL squared plus LK squared. Okay, and we've gone over examples like that before, so I'll leave that with you. Okay, let's move on to the next example here. This one just asks us to solve for the hypotenuse. So this is an unknown value to the nearest meter. Okay, so again, in this case, we know JL. It's 10 meters. And this is opposite, again, using a vertex K. So we don't know the adjacent side, but we don't need to know it. So I would stick with just, in this case, because the unknown side is the hypotenuse, we're going to use the sine, which is an operation done on an angle. And in this case, that operation always yields a ratio, which for sine is opposite over hypotenuse, and that would be 10 all over JK. And from there, solve by, working with that equation. So what we have here is a little bit of a twist because the unknown is in the denominator. So what I would suggest to do is either use one of two approaches. One approach is to look at this equation and say, okay, I can cross multiply. Cross multiplying is something that's often done when we want to sort of pull a unknown out of the denominator, and then we can divide both sides by sine of 30, and that would give us 10 over sine 30. Okay. Another alternative here is to flip both of them, and we can do this mathematically. We can take the reciprocal of both sides, okay, and the reciprocal of a fraction is just flip the denominator and numerator, so it inverts them. So now we have 1 over sine of 30, and just take note that whenever you don't have a denominator visible, it's always 1, okay, so that makes it easy to think of it as a fraction, okay. So we flip both fractions, and that they're still going to be equal, okay, just a little bit like we could say 2 is equal to 4 halves, and if we flip both sides, we get 1/2 equals 2/4, and well, the fractions have changed, but the information is still equal, okay. So that's the important part here, is that we still have an equivalence, and now we could just think of that as, okay, to clear the fractions, we'd multiply both sides by 10. 10 times jk over 10 equals 10 times 1 over sine 30. Okay, and in this case, of course, you're going to end up with the same result as we had in the original approach, okay? So 10 divided by sine 30 would be equal to the hypotenuse, and that's sufficient. So I'll leave that with you to calculate. I'm not as concerned about the actual answer, but just how do we get it. Okay, so for this one, we're trying to find the length of P, and this would be the height of the triangle. I'm going to be even less explicit here, and I'm just going to outline the general steps here. We know that P is, again, opposite to 60 degrees. 225 is the hypotenuse, and then from that, therefore, with those two sides, use the sine ratio. Okay, and from there you should know what to do. Set up the equation using 60 degrees and the side lengths in their appropriate spots. Okay. Okay, in this last example here, for the questions which would require you to solve for length, information is given but a diagram is not. So what I'm going to have you do is read the example, try to draw the diagram. I'm going to pause my video, and then I'm going to draw it, and you'll come back and you'll see the setup. Okay, but I encourage you to try to generate a diagram based on that information. If you can't do that, you're going to be unable to solve a lot of trigonometric questions. So draw your diagram and then compare it to mine. Okay, so I just grabbed a picture from the internet. This is the House of Commons in Ottawa. That's the Peace Tower. So it just gives you an idea. If you're standing 30 meters away from the base on the lawn there, you're looking up using a clinometer, angle gun, or something like that. You know, you can measure angles approximately. But to be really exact, maybe an instrument is measuring the 72-degree angle, and you're pacing out 30 meters, just approximating knowing your stride length, and you can get a pretty good estimate of the height of a building, okay, without actually going to the top. So that's the information that we need to label. We have the height. We can set up a ratio here. So again, keep in mind what you're given. Keep in mind what is unknown. Try to identify the trigonometric ratio which would apply, which in this case is the tangent, because the opposite is the height to the 72-degree angle, and the adjacent is the 30-meter value. So we can again here set up a ratio similar to the ones before. Tangent of 72 degrees equals opposite over adjacent, and that is the unknown height divided by 30. Notice in this case, there's no need, just my sloppy penmanship. There's no need to label this triangle necessarily. If you wanted to, you could label it something like this. Capital H here, that's consistent with height. Little h, you could label it HIJ if you wanted. If you need the vertices labeled, if that really helps, do so. But if you can see it as a triangle with sides that don't necessarily need corner labels, then for this type of question, that's appropriate. Okay, so let's move on and look at situations where we're trying to solve for an angle. Okay, again, this you should have done before, but I'm going to spend a little bit more time on this because it involves some operations which are different, and it also involves this concept of inverse or opposite operation. So the first thing you need to take note of, there's a little bit of a mistake in my note here. It came up, I had it all looking nice, and then I opened up my notebook file and all my angle symbols were turned to P's. So I had to adjust, I didn't catch that one. So for an angle that's less than 90 degrees, which is an acute angle, we can use inverse ratios, or what are called inverse trigonometric ratios, in a right triangle to solve for angles. And this is a little bit awkward the way it looks, okay? But what we end up doing with this method is we're solving for an angle by taking a ratio of side lengths and taking the inverse sine or inverse cosine or inverse tangent of that ratio. So in this method, we need to know two side lengths, and we're using that information to solve for an angle. Previously, we used an angle and one side length to solve for an unknown side, okay, which would have been part of the ratio. So the key thing here is that this uses two side lengths. Okay. Now, if we used the different ratios, we could modify those calculations to solve for a different angle, namely B in the triangle given. The key concepts involved in this work with inverse ratios is that these pairs, sine and inverse sine, cos and inverse cosine, tan and inverse tangent, they are opposite or inverse operations. It's very comparable to the square root operation versus the square operation. That would be an example you would be familiar with. The use of the superscript as -1 can be a little bit confusing. It's just a symbol to represent the idea of an inverse, and it's just put in that location just to kind of make sure you don't confuse it with multiplication. It's not an exponent. The reason why I think -1 is used is that because it brings up the idea of opposites, because you think of 1 and -1 are opposite numbers or inverses, and that's what's intended here, is that when you see that -1 attached to the trigonometric operator, you're applying the inverse. And your calculator will do this using probably a second function or a shift key, and you need to locate that set of 3 buttons in your calculator and be familiar with how to use those. Okay. The next thing I want to mention is that both groups of operations, the regular primary ratios, sine, cosine, and tangent, and their inverses, they perform a function on a number. So we want to be consistent when we're writing down our work. We understand that when we write sine, this is an operation on something. So we just don't write sine. It doesn't mean anything. We have to always write sine of an angle. Similarly, we don't just write inverse sine or inverse cosine or inverse tangent without a number. It has to be attached to a number. Okay, so these are operations. The first group, sine, cos, and tan, they all calculate the ratio of side lengths for a particular angle. They never calculate an angle. Okay, so the ratios that they, of course, give you, we know that. SOHCAHTOA helps us to remember that set of 3 ratios. For their inverses, it's the same ratios, but in this case, the second group of operations, they all calculate an angle for a particular type of ratio. They never calculate a ratio. Okay. So whenever you're using the primary ratios or primary operations, you're always trying to find a ratio. If you're using the inverse operations, you're trying to find an angle. So let's look at one example here that will help us to apply this. Before we look at this example, just need to know one more thing. Besides angle of elevation and angle of depression, you may come across questions that have a bearing involved. It's just a compass bearing that we're referring to here. It's just an orientation or an orienteering idea. And the way it works, pretty simple. It's on the horizontal plane. So just picture walking around in the forest, and you've got a compass. The ground is your horizontal surface, and that the bearing would apply in that situation. So you're looking at north. Say magnetic north on a compass is being detected by the compass magnetic needle, and the bearing is measured clockwise from north. So if you are walking due north, you're walking on a 0-degree bearing. If you are walking due south, you're walking at a 180-degree bearing. Southwest, for example, is 225-degree bearing. Due east, 90. Northeast, 45. Northwest, 315. Okay, so this just uses a full circle, and angles are always measured clockwise from north, which is 0. Okay, if you've gone around full rotation, you'd call that 360 degrees, but really you're at north again, which is 0-degree bearing. Okay, so this is the last example I'm going to look at, and then tomorrow and the next couple days we'll probably be doing some hands-on work with clinometers and measuring inaccessible heights, and then we'll also be getting really good at solving real-world problems with trigonometric ratios. Okay, so this example number 5, the plot is drawn. Michelle is drawing a map for a parcel of land or a plot of land. There's two things we have to find. One is the angles in the triangle, both angles that are not known, and the bearing of the third side of the plot, which is shown here, kind of a little bit hard to see exactly where that is, but if you know that this is due north, if one side of the plot of land is due north, then we would be able to say that the line connecting vertices A and B would be a bearing. Okay, so this is what we need to solve for, is this angle here. Well, that's not an angle inside the triangle, so that would mean that we would need to know the angle at vertex A, which is inside the triangle, and then we can use straight line property, and we'll get to that as we wrap up. So the two angles that are not known here, keep in mind, we have side information. So when you see a triangle and you don't have an angle besides the 90, you should assume you're going to have to use an inverse operation, which, as we said, was using two side lengths. So that you want to pick up on some of the things that are going to help you to know, when do I use sine or inverse sine? When do I use cos or inverse cos? When do I use tan or inverse tangent? Here our angle is unknown, so we should be thinking in terms of an inverse operation. So let's label the side lengths relative to a chosen angle. So I'm going to use, why not just go directly with vertex A, and from A we would say that CB is the opposite and AC is the adjacent. Okay, so that means that we're going to use tangent, and the tangent of vertex A is equal to CB over AC, which is again opposite over adjacent, and we have both of those known numerically, so it would be 1.8 divided by 1.2. I'm going to leave the units out here because the angle is not in kilometers, so we'll pause, calculate that, and that will give us the first angle. If you're already thinking ahead, you know that the angle B, which is the third angle in the triangle, again, would just be equal to 180 degrees, subtract 90, because we've got a right angle here, subtract angle A. So once we know angle A, we can solve for angle B. All right, I'm back now. I hope you had a easy time with this. Keep in mind your ratio is a fraction, but often we want to just figure out what that is as a decimal. You don't really need to do that in your calculator. You can just start out with the inverse tangent of, and then just put 1.8 divided by 1.2 in brackets. You don't really need to know what that is. However, in this case, I found that it was 1.5, so it's a nice clean fraction to work with. And the angle, of course, is the inverse or opposite operation to tangent. So tangent of the angle gives the ratio. The inverse tangent of the ratio gives the angle. Okay, and just remember, we're going back to what was outlined here. So when you have the ratio, or maybe the ratio looks like this, as we saw, then when you apply the inverse operation to it, you get back the angle. Okay, so in our example here, our angle is 56.3 degrees for angle A, so that means angle B would be the third angle in the triangle, which I worked out to 33.7 degrees. Keep in mind we're approximating here, so dot above the equal sign, rounding. And the exterior angle A, we've got to be careful here when we say angle A, because in this diagram there are actually two angle A's, but with regards to triangle ABC, I think we can safely say that in triangle ABC, there's only one angle A. And the exterior angle A, which is our bearing, is going to be 180 subtract 56.3, and that's due to the fact that there is 180 degrees in a straight line. And the bearing in that case is just supplementary to 56.3. It's the one that would add to give 180. So that closes off the last example. Sign work here is to read example 3 on page 7. Discuss parts from 1 to 6 with a partner for basic understanding. That we'll do in class. And then also in class, you'll be looking at problems 7 to 14 on pages 9 to 12. You're welcome to get a start on that. But again, your commitment for this class for now is to be viewing the lessons outside of class time and then working on the problems during class time. So hope to see you tomorrow, and bring any questions you may have. Thank you.